design of combined footing. Let's take a problem. Design a combined footing for column C1, this is column C1, and column C2, this is column C2, of size 300 by 600, 300, 600, 300, 600. The factor load and moments on C1, this is C1, our actual load P1 is 1200 kilonewton, 1200 kilonewton. MUX1 is 100 kilonewton. M by 1 is 75 kilonewton meter. The factor load and moments on C2, this is C2, are PU2 over here is 1200 kilonewton. MUX2 is 100 kilonewton meter. MUY2 is 75 kilonewton meter, right? So use M20 grade concrete and Fe415 steel. The effective cover of bottom is 75 mm. Okay, the effective cover over here is 75 mm. Okay, a load factor considered is 1.5 and the SPC is 250 kilonewton per meter square. Okay, so this is our combined footing. Okay, this cantilever is 1 meter. The span of this cantilever is 1 meter. The span of this cantilever is 1 meter, and this is 3.4. Okay, so this distance is 1.3. This is 4 meters, and this is 1.3. Total is 6.6 meters. Okay, this is given to us. Now we will take a projection of 150 mm on both the sides. So we will assume the width of the beam as 600 mm. Okay. So now let's start the design of this problem. This type of footings are very commonly used, okay, in practical fields. So given to us, okay, soil bearing pressure SBC 250 kilonewton meter square per meter square. Length of footing is 6.6 meters. 6.6 meters, okay, right. Column size C1 300 by 600. Okay, 300 by 600. Column size C2, 300 by 600. 300 by 600. Okay. Now, width of the footing, we are taking a 600 mm. 600 mm. Okay. Now, effective cover 75 mm. 75 mm. Okay. PU1 is 1200 kilonewton, MUX1 is 100 kilonewton meter, MUY1 is 75 kilonewton meter, PU2 is 1200 kilonewton, MUX2 is 100 kilonewton meter, MUY2 is 75 kilonewton meter. Fi is 415 Newton per mm square, FCK is 20 Newton per mm square. Now, first step is we have to assume the width of the footing. The width of the footing is unknown to us, right? So, total service load P on the footing is 1200 plus 1200. 1200 is PU1. This is PU2. Okay. PU1 acting over here. This is PU2 acting over here. Okay. Divided by 1.5. These are factor loads. Okay. So divided by 1.5 is equal to 1600 kilonewton. This is R actually. Okay. Service load. Okay. Resultant of this two. Okay. Acting at the CG of the footing. The approximate weight of the footing and the backfill delta P is taken as 10% of this load, that is equal to 160 kilonewton, right? Now SBC allowable should be greater than or equal to P plus delta P divided by area, but we have moment in both the directions, so it has to be plus mu x by zx plus mu y by zy. Okay, but for simplicity of calculation, I'm just taking P plus delta P divided by area. P is known 1600, delta P is 160, L is 6.6, and B is to be found. So SBC allowable is 250 kilonewton per meter square. So B is found to be 1.06 meter. But as we know that moments are acting in both the directions, that is major and minor on the footing. So I will assume a larger B than this. So I am assuming it as 1.6 meters. Okay. Right. Now after assuming the B, okay, now the first step is we have to check whether the actual pressure under the footing is less than allowable. Okay. So check SBC allowable is greater than SBC actual. Okay. So first we have to find the Ex and Ey. Okay. This forces, okay, the load and moments on this column, the load and moments on this column can be resolved about CG, right? So you will get a one resultant force and one resultant moment in about major axis and another resultant moment about minor axis, right? So for that you have to first find Ex and Ey, right? So we can see in this figure that the resultant force R is found to be acting over here, and this distance is Ex and this distance is Ey. So when you multiply R into this distance, you get the resultant moment about CG over here, that is about major axis. When you multiply this resultant into this distance, you get a moment like this about minor axis. Okay, so that will be your resultant moment, right? So that is how you can resolve the forces about CG, right? Now we will find Ex. Simple. Ex is equal to Mux divided by P plus delta P. Mux is nothing but Mux1, Mux1, okay, that is 100, okay. Muy1, sorry, Mux2, this is Mux2, Mux2, okay. So that is also 100, right? So we get 100 plus 100, that is these are factored loads, okay, so divided by 1.5, and these are working loads, okay. So you get eccentricity Ex as 0.07575 meters, okay. So Ex is equal to 0.07575 meters, okay. Now let us find Ey, okay, that is Muy divided by P plus delta P. Muy is Muy1 plus Muy2, okay. This is Muy1 plus Muy2. Both are 75 kilonewton meter. Okay, 75 plus 75 divided by factor 1.5 divided by P plus delta P. That is our working load and the weight of the backfill and the footing, that is delta P. Okay, so this turns out to be 0.05682 meters. So this is 0.0582 meters, right? So this is how we find the eccentricities Ey and Ex. Okay. Once you have found that, then you can easily find Qmax. Okay, Qmax is P plus delta P divided by area plus Mux. Mux is this. This is Mux, right? Mux divided by Zx and Muy, this is Muy divided by Zy. Okay. So P, Mux, Muy are working loads. Okay. So we can see we find Q maximum equal to 213.659 kilonewton per meter square. So this Q max has to be less than SBC allowable. So SBC allowable is 250. We get Q max as 213.659 kilonewton per meter square, which is greater than this. So the size of the footing is okay. Now we have to find Q minimum. That is the second stage. Okay. Q minimum is again P by A minus Mux by Mu Zx, Mux by Zx minus Muy by Zy. Okay. So this is found to be 119.68. As this is positive, so it is fine. Okay. That means full footing is in contact with the soil as there is no negative pressure below the footing. If if this space was found to be negative, then you will have to increase your width or increase the area of the footing, because negative pressure below the footing is not allowed, right? But this is positive and this is positive, so it's okay, right? Now, eccentricity due to factored load and moments, okay. So this is about the length, that's major axis. This is 6.6 meters. We find resultant R over here, okay. This is this load is 1200, this load is 1200. This is on column C1, this is on column C2, and the moment on the column C1 is 100, on a moment about column C2 is also 100. This both the moments are about major axis, right? So we get a resultant R, okay, at a distance 3.2167 meters from this face, right? And see, this is CG, okay. So this is 3.3 meters. So EX is 3.3 minus 3.2167, right? Similarly, about major axis, this is CG, this is 1.3. R is found to be 1.2375. So EX is 1.3 minus 1.2375. Okay. So this is due to the eccentricity is due to the factor load in moments. Okay. Right. Now comes the next step, that is we have to find the factor net soil upward pressure below the footing. for which we have to design the footing, right? Okay. So Q maximum is R. R is nothing but PU1 plus PU2, right? This R is the resultant of both the loads acting at the CG divided by A plus MUX by ZX. Okay, MUX we know that is moment MUX1 plus MUY1, that is 100 plus 100. Okay, and MUY2 is MUY is MUY1 plus MUY2, right? That is 75 plus 75, 150, right? Over here we have to take factored load because we are finding factored net upward soil pressure. Okay, so putting this value over here, we get Q maximum as 297.76. Okay, so this is 297.76. Okay, we can see over here, R is the resultant acting at the CG. This is MX, that is MUX. Okay, MUX is the resultant moment about the major axis, so that will be acting over here. And MUY, okay, is the resultant moment about minor axis, which will be acting over here, right? Okay, so this is acting in this direction, and this is acting in this direction. So obviously, the Qmax will come at this age, right? So this at this age, the Qmax is 297.76. Now Q min is nothing. There's R divided by A minus MUX divided by ZX minus MUY divided by ZY. Okay, so that is 156.79, which will act over here. This is the upward soil pressure, minimum upward soil pressure, which will be at this age, right? Okay. Now Q1. Q1 is R by A plus MUX by ZX minus MUY by ZY, which is 191.23. Okay, so that will come over here at this age, right? Now Q2 is R by A minus MUX by ZX plus MUY by ZY, which is 263.33, and which is found to be acting over here, right? So this is our actual pressure diagram below the footing, upward soil pressure diagram below the footing, for which we will have to design the footing. Okay, so first step, okay, we will do the design of cantilever slab. Okay, this is the cantilever slab, and this is the beam. Okay, now in case of cantilever slab, shear will be the governing factor, which will set the depth of the footing, right? So we will design this cantilever slab as a 1 meter design strip. Okay, this is 1 meter wide design strip of the cantilever footing. I have taken it over here because over here the upward soil pressure is maximum. Okay, so we are designing the strip for the maximum upward soil pressure, right? So assuming that in this 1 meter strip, the total upward soil pressure is 297.76. Okay, so this is the pressure over here, and this 191.23 is the pressure over here, right? So this is the cross section through 1 meter wide design strip of cantilever. This is the cross section through this 1 meter wide strip. Okay. Now this is our beam, central beam, 600 width, and from here, from the face of the beam to the edge of this cantilever slab, the distance is 0.5 meters. This is 6.6 meters. This is 1.6 meters, right? Now we have to first assume our d dash. Okay, so as we as I just told you that in case of cantilever slabs footings, okay, the shear going to be the are going to govern the depth of the footing, right? So taking one way shear, for one way shear, the section is taken at a distance d from the face of the support or face of the beam over here. Okay, this is some kind of strip footing. Okay, beam is running throughout the footing, so you will not have any you don't have to check for the punching shear stress. Okay, you only have to check for the one way shear stress. So this is the cross section for one way shear. Okay, at a distance d from the face of the beam. Okay, so we don't know d dash. Okay, we have to assume a appropriate d dash. Okay, so starting from the from the assumption that uh, we will design 1 meter strip with maximum factor net pressure below the footing as shown in figure above. Okay, so first we will assume our tau c to be 0.36 newton per mm square, and for fck20 from table number 19 is 4562,000, we get pt is equal to 0.25 0.25%. Okay, so we are assuming that at this section this tensile steel is 0.25%, right? Now, so we allowable the section which this the, this cross section can take, the shear force which this cross section can take is equal to tau c, the permissible shear stress, into d dash into 1 meter strip, right? So that will be your allowable shear force which this section can carry. Okay, so we'll make our first equation, that is V allowable is equal to tau c into B into d dash, where B is equal to 1 meter wide design strip. That is our equation one. Okay. Now finding average stress in from the above figure, Q average. Okay, so finding fee, if you want to find Q at this section, then you need to know D. Okay, but D is still unknown. So what we do, just for the case for assumption of D dash, we take an average stress diagram. Okay, it's an assumption just to get an appropriate D dash, right? So we assume this to be average. So this average is 244.495 kilonewton per meter square. Okay, so Q average we are assuming is just 244.495 kilonewton per meter square, right? So due to this upward soil pressure, you will have one force over here, right? That is V actual, okay? Shear force V actual. That V actual has to be less than this, right? Then only the footing is considered to be safe. So we are assuming that this V actual is equal to this V allowable, and the equation for this V actual will be Q average into this. This distance is, this is zero point 0.5, okay? This is zero point 0.5, right? So this is also zero point 0.5 meters minus D. So this is zero point 0.5 minus D, right? Into 1 meter. So this is how we get the uh, another equation. Okay, V allowable, or you can say V actual is equal to Q average into zero point 0.5 meters minus D dash. Okay, this is D dash, and my into 1 meter wide design strip. So now equating equation 1 equal to equation 2. Okay, so this is the formula, right? We get D dash is equal to this D dash, we get equal to 202.23 mm. So let us assume D dash is equal to 210, right? Because we know that there are chances, okay, that this D dash might uh, might not be appropriate. Okay, so to be on the safer side, we are assuming a rounding of this figure to 210 mm. Okay, now we can see over here that if this depth is 210, then as we go towards the center, the footing depth increases, right? So we will take the overall depth of the footing, means of the cantilever slab. Okay, overall depth of the cantilever slab at the face of the beam equal to 450, right? So we have taken, assume assume the overall depth d at the face of the beam as 450. So that is what we are assuming, right? Now we can find effective depth d over here. Okay, we know this effective cover is 75. So 450 minus 75 gives the effective depth d. Okay, so d minus 75 is equal to 375 is our effective depth d over here, which is this, right? Now we know this D, so we can find this Q. Okay, so this is zero point 0.5 minus 0.375, right? Zero point 0.5 meters minus D, D is 0.375. So now you can find Q. Okay, so Q is found as to be 289.43 kilonewton per meter square. Okay, this Q is found to be 289.43 kilonewton per meter square. This is found by interpolation, right? You know this, you also know this, right? So you can easily find it. Okay. Now, once you know Q, you can find your actual shear force. Okay, for finding shear force, simple. Take this plus this divided by 2 average. Okay, we can average this and turn it and convert this into a rectangle. Okay, so average 297.76 plus Q, that is 289.43 divided by 2 into this is the length, that is zero point 0.5 minus 0.375 meters, okay, into 1 meter is the width, okay, 1 meter is the width, okay. So we get shear force V equal to 36.7 kilonewton. Now, as in case of cantilever footing, we do not provide shear force, okay. So our nominal shear stress tau V should be less than tau C. If it is not so, then either you will have to increase the depth of the footing or increase the percentage of tensile steel. Okay, so let us check. Let us first find the nominal shear stress tau V. Okay, so tau V is equal to V divided by BD dash. Okay, okay. So we are finding at this section, right? Okay. So whatever shear force which we get from here, we actually will be acting over here, and that is to be taken by this section. Okay. So this is your depth D. Okay. So this strip. Okay. So we have to take the cross sectional area of this. So this is 1 meter is the width and depth over here is D dash, right? So the area of this cross section will be 1 into D dash, right? So V divided by the area of cross section. So that V is equal to 100 mm because we are assuming 1 meter design strip. So this is equal to 0.1748 Newton per mm square, which is less than tau C 0.36 Newton per mm square. So safe. Okay. So we have considered the corresponding PT equal to 0.25% at this section. Okay. So we will continue with that. Okay, that assumption, right? Now, calculate moment and main steel reinforcement for cantilever slab. So for calculation of moment, we have to take a section at the face of the support, that is at the face of this beam. Okay. So simple, everything is known. D is known to us, 450 mm. This is also known to us. This is zero point 0.5 meters, zero point 0.5 meters. Okay. Q you can easily find at this section. Okay, so Q is found to be 264.47 kilonewton per meter square. Okay, this is meter square. Okay, okay, please don't get confused. Okay, so this is known. This is known. The Q is can be found, that is equal to 264.47 kilonewton meter square. The finding moment. Okay, so this is your upper soil pressure diagram, which will give a moment about this section, right? So we can divide this upper soil pressure diagram into two parts. One is rectangle, other is triangle, right? So this rectangle upper soil pressure will give a force Q into zero point 0.5 into 1 meter, right? That force will act this CG, and that force into L1 by 2 will give you the moment about the section. So that is equal to this, gives that value, right? Now taking the triangle portion, this minus Q, okay, this is this, Q is 264.47 minus, okay, so into zero point 0.5 into zero point 0.5 gives the area of this triangle, and into 1 meter gives the total area of the uh, width for this 1 meter width strip. Okay, and that gives us the force because we are already multiplying the Q. Okay, that force will be acting at over here at the CG. This force into this distance will give you the moment. Okay, so that is this. So we get this moment total equal to 35.84 kilonewton meter. Right? Now we find the AST using this formula. B is equal to 1 meter, that is 1000 mm, and D is equal to 375 mm, right? So AST found from this formula is 268.84 mm square. Spacing center to center, we are going to use 10 mm dia bars as our main steel. So the area of this bar is 78.5 mm square, right? So that gives us the spacing 292. So let us provide 10 mm dia bar at about 275 mm center to center. So EST provide definitely will increase as we are reducing the spacing. Okay, as we are reducing the spacing, definitely the EST provided will increase. Okay, so the EST provided is found to be 285.5. But if you remember that we have taken considered 0.25% steel for the shear criteria, right? So we will continue with this 0.25%. This area of steel is found to be less than 0.25%. So okay, so 0.25% steel is found to be we have to take D dash over here, okay? Because we are finding the steel at this section, okay? So D dash at this distance, the effective depth of the footing is D dash, okay? So 0.25 into B into D dash is equal to 525 mm square, okay, which is greater than this. So we'll provide this area of steel, okay, for what for per meter. This is the area of steel required per meter width of the cantilever slab footing, right? Cantilever slab. So center to center spacing required is 1000 into area of 10 diabar, okay, that is 78.5 divided by ST provide is 525, okay, so that is equal to 149.5 mm. So let us provide 10 mm dia about 145 mm center to center, okay. So let us see how it is provided in the detailing, okay. So we will see the detailing just okay, you can see over here. So this is section 1 over here. This is section 2 over here. This is section 3 over here. Okay. These red dots are the main reinforcement of the cantilever uh, slab footing, right? So this is the main steel for the cantilever slab footing, right? Okay. So this we are going to provide 10 mm dia about 145 mm center to center throughout the length of the footing cantilever slab reinforcement. Okay. So this is how we show this in this detailing. Okay. Now we will go to design of beam. Okay. So this is how we did the design of footing, and we found that our footing slab is safe in shear and bending moment. The steel provided is adequate and enough adequate for taking the moment coming at the face of the beam, right? Now, design of beam. So this is our actual upward soil pressure below the footing, right? So we can simplify by just taking the average. Okay, take the average of this 191.23 plus 297.76, that is 244.5 kilonewton per meter square. Okay, this is in kilonewton meter square. Now you can average this too, which is 210.05 kilonewton meter square. Okay, so this is now our modified upward soil pressure, which we will consider, okay, for designing the beam. Okay, so factor net soil pressure for soil distribution below the beam. Okay, now beam we are considering is a line element. Okay, so this say this is say a beam. Okay, because we are considering beam as a line element. So we will convert this pressure that is in kilonewton per meter square to kilonewton per meter. Okay, so because we want the loading in this direction, because we are considering this beam as a line element. Okay, so how can we do that? This pressure into 1.6. Okay, that will give you 336.08 kilonewton per meter. So that is the load over here. Okay, similarly 244.5 into 1.6, that is equal to 391.2, that will be acting over here, that is over here. So below this line element, that's beam, we will have a loading like this. Okay, it's kind of trapezoidal loading in kilonewton per meter. Okay, so now the case becomes a little bit easy. Okay, so this is our column 1, on which we have our PU1, that is factor load is 1200, and the MUX1, that is factor moment is 100. This is our column C2. Okay, the point load is over here. PU2 is 1200 kilonewton, and the moment factor moment is 100 kilonewton meter. Right? So this is total length 6.6 meters. This is 1.3. This is 4 meters. This is 1.3 meters. Okay. Now I have given a table, complete table over here, which shows the bending moment, shear force. Okay. Uh, this is bending moment. This is shear force. Don't get confused. This is steel. Okay. This is EST minimum, and this is spacing of four leg shears. Okay. So for different distance, okay, I have taken distance from point 1 to 6.6 and with increment of point 0.1 meter, okay, from left to right, okay. So this are the moments at this distance and shear force at this distance, okay. So how can we develop this table? Okay, so let's take an example. Okay, this is why. Why is the upper soil pressure ordinate at a particular distance x? Okay, so we will take at a distance 1.3. Okay, so we want to find the moment about this distance and the shear force at this section, moment and shear force at this section due to this upward soil pressure. Okay, so first we have to find y. So we can find y by this formula. Okay, so q2 is this, q1 is this. Okay, 6.6 is the length. Okay, plus q1 that will give us y, okay, into x. Okay, so we want to find the y over here, so where x is 1.3 meters. So putting the values, we get y is equal to 346.93. This is 346.93. Okay, so once you get this y, you know q1. Divide this trapezoidal into two parts, rectangular and triangle, and you can find the moment. So moment due to this rectangular upward soil pressure will be q, okay, that is q into 1.3, that is the force, okay, that force into L1 by 2, okay. So you get that moment by this values in the bracket, right? Now another, it will be due to this triangular portion, that is y minus q1, y minus q1 into 1.3 into zero point 0.5 is the area of this triangle. That is force, okay. That will give that is force, you can say, okay. So that force will be acting at this point, that is this CG, okay. That force into L1 divided by 3, okay, that is this value, okay. So that will give the moment due to this triangular pressure diagram, okay. So this force is going to give a clockwise moment. This force is going to give a clockwise moment, and uh, our moment acting over here is also clockwise, right? So this will be added to this, both to this moment. So plus 100, okay? This is plus 100. So plus 100. So this total moment is 387 uh, kilonewton meter at a distance 1.3, right? 1.3 meters. So let us see this in our table. At 1.3, the moment is 387, okay, which we got from which we saw how do we get this value, right? Now we have to find shear force. Simple, okay. You can take the average q1 plus y2, q1 plus y divided by 2. That is your average stress, and that will directly give you the shear force. q1 plus y divided by 2 into 1.3, that will give you the shear force. This shear force is acting upward, okay, and over here the load is acting downward, right? So we are finding the shear force at this section, okay. So this minus this, okay, this is minus, this is positive, this direction is considered to be negative, and this is considered to be positive, okay. So over here this is minus plus 1200. So this gives you 756 kilonewton. So V, you can see that at 1.3 it is 756. Okay. So this is how this whole table can be developed by taking different distance, finding y, and finding the moment and shear force at the particular distance. Okay, you can develop this table. Okay, so this was just an example or sample that to explain that how do we get this table. Okay, so now let us proceed further. Okay, so this is the bending moment diagram and this is the shear force diagram. Okay, now let's start the design. So now first step is we have to find or we have to assume the depth of the beam. Okay, so for that we have to take the maximum moment acting on the beam. From table we get the maximum moment is 422.9 at a distance 3.4 from left. Okay, at a distance 3.4. Okay, the maximum moment is 422.9. So we will find the depth for this maximum moment. Okay, depth of the beam for the maximum moment. Okay, so we know that the formula for finding the D balance, okay, is equal to mu is equal to 0.138 FCK BD square when the grade of concrete is M20 and Fe415. Okay, so from that we get D equal to 505.34. So this is the minimum depth that is to be provided. So we have to take a higher depth so that the section is under reinforced, right? So let us assume the overall depth of the beam as 750 mm. Okay, 750 mm is the overall depth of the beam. Okay, so overall depth we are taking as 750 mm, top to bottom, right? Okay. Now effective depth D is overall depth minus effective cover. So for beam, we are taking effective cover as 100 mm. Okay. So let me explain how. Okay. So let us go to detailing part. We have taken the effective cover in case of this cantilever slab is 75 mm. We can see the main steel of the beam is above this cantilever steel. So the depth effective cover for this beam will be greater than 75 mm. So we are assuming that as 100 mm. Okay, so we are taking effective depth as overall depth D minus 100. Okay, that is what we are taking, right? Okay, so that turns out to be 650 mm. So effective depth of the beam is 650 mm. Okay, now, the next step is to find EST minimum. B is known 600, width of beam. D is known 650. Fi is known 415. That is 800 mm square. Okay. So whatever steel we provide should be greater than 800 mm everywhere in the whole, everywhere in the any section that you consider in the whole beam. Okay. So over here in table, I have taken uh, AST minimum was 800. Okay, so the steel provided should be greater than this AST minimum. Okay, now coming to the next point is tensile steel required for the face at the face of the column for the cantilever beam at left 1 meter from left. This is distance. Okay, so cantilever at left. Okay, so this is our footing. This is cantilever at left. The span of this cantilever is 1 meter. So we will find the shear force at the at distance 1 meter from left from the table. Okay. Uh, Sorry, we will find the moment. Okay. We'll find the moment at 1 meter uh, distance from the left. Okay, because we are designing the tensile steel. Okay, so at 1 meter, the moment is 169.4, okay, kilonewton meter. So coming back to over here, okay, so moment is 169.4 kilonewton meter. We are finding tensile steel required at the face of the column for the cantilever beam at left. So we have to consider the moment, okay. So this is the moment obtained from the above table using this formula where B width of the beam is 600, D is effective depth of the beam that is 650. We get required area is 752.3 mm square. So let us provide four numbers of 16 mm dia bars whose total area is 804 greater than this. Okay, so we will provide that steel over here. Okay, so this is our cantilever, and this is our main steel. So we will provide four numbers of 16 dia. Okay, so this is our deflection diagram. See, this cantilever will deflect like this. This central beam will deflect like this, and this cantilever will deflect like this, right? So over here the tension is at bottom. Over here the tension is at top. Over here the tension is at bottom. So in cantilevers the tension is at bottom. So the main steel will be at the bottom, and in middle central beam, okay, the tension is at top. So the main steel will be at top. Okay. Okay. So this is how we provided four numbers of 16 dia for this cantilever at left, right? Now coming to the next step, that is uh, tensile reinforcement required at the face of the column for cantilever beam at the right. That is the distance 5.6 meters from the left. Okay. So beam at the cantilever beam at the right. This is cantilever beam at the right. This is the face of the column, and this distance is 5.6 meters. So we will find the moment at this point from the table. Okay. So from the table, we get moment equal to 5.6 is the moment is 193.2 kilonewton meter. So we will take that, okay, 193.2 kilonewton meter. Using this formula, we get AST is 863.3 mm square. We will provide five numbers of 16 diabars. The total area provided is 1005, which is greater than this, so it is safe and okay. Over here, I have intensely taken the diameter of bar 16 because I want to keep the diameter in both the cantilevers same. Diameter of bars in both the cantilevers to be same, so it becomes easy for curtailment. Okay, so I have intensely, deliberately taken the diameter in the in the second cantilever is also 16 bar, right? So this turns out to be five numbers of 60 diabar. So we can see, okay, I have provided five numbers of 16 diabar. Okay. Now, the reason for keeping the diameter same in both the cantilever is because this is a cantilever, right? So the development length for this bar has to be at least 1.5 times the span of the cantilever, right? So this is 1 meter span into 1.5. So at least this bar has to be taken 1.5 meters inside all these bars. Similarly, all these bars has to be taken 1.5 meters inside this central beam, right? So the distance in between is not much. So what can we do? We can run four numbers of 16 diabar throughout the beam, okay, and the another one bar remaining, you can run that bar up till the end of this support, right? So this is how we detail the bottom steel. Okay. Now coming to the next step. Okay. Tensile steel required near the midspan of the central beam. Okay. The maximum moment is at distance 3.4 meters from left. Okay. So let us see the moment from the table. 3.4. Okay. The moment is 42219. So let us find the steel for that. Okay. And moment is 422.9 kilonewton meter. So AST obtained is 2020 square. We will provide four numbers of 25 diabar plus one number of 20 diabar. So the total area is 2276.5 square, which is greater than 2020. So it's okay. So we will provide 425 plus 120 diabar in the central beam. Okay. Now we can see that in case of cantilever, okay, the top steel is not required. Okay, so you have to provide minimum because the tension is at bottom and this is in compression zone, right? Uh, so we can you have to provide at least 30% of this steel over here. Okay, so we have decided that the steel over here is four numbers of 25 diabar plus one number of 20 diabar. But after this, we will continue 225 plus 120 diabar in both the cantilevers. That means we will curtail 225 diabars over here. Okay, over here and over here, and the continuing bars will be 225 plus 120 diabars in cantilevers. So how do we decide that at which point these two bars should be curtailed? That we'll see later on. Okay. So this is how we have detailed our reinforcement. Okay. Now we can see this section. Section 1 1. Over at the bottom you have four 16 diabars. So 1, 2, 3, 4 bars. At top you have three bars, 225, 120. This is 25. This is 25, and central bar is 20 Over here, at bottom you have five numbers of 16 diabar, five numbers. At top you have five numbers, that is 425 diabar and 120. So 1, 2 and 1, 2, 4, and central, this is 25 and central is 20 right? At section 3 3, you can see five numbers of 16 diabar, five numbers, three numbers, 225, 120, 225, and central one is 20 okay. So this is how you can do the detailing of this footing, right? Now let us do the check for shear, okay. Okay, coming to the check for shear, that is next point. Check the shear at the face of the cantilever at left at a distance 1 meter from the left. So let us find the shear force from the table at 1 meter. Okay, 1 meter. The shear force is 340.3. Okay, 340.3. So we will take the okay shear force V is equal to 340.3. Now area of steel provided is 804. Okay. So the area provided at this section, tensile area provided at this section is four numbers of 16 diabar. So the area of this is equal to 804 square, right? So that is what we have taken, area provided. Simple, find PT. Okay. So you know everything. PT is found to be 0.206%. Okay. Now permissible shear stress is found to be 0.318 for this PT and M20 from table 19 IS 456 2000. Okay. Now nominal shear stress. Nominal shear stress is V divided by BD. B is this. B is 600. D is 650. So that is 0.8725. Now tau V is greater than tau C. Okay. Sorry, this is tau C. So we will have to provide shear reinforcement. But please remember, our tau v should not be greater than tau c max. Tau c max is 2.8 Newton per mm square. So it is less than maximum. So it's okay. So now we have to find the spacing. We are going to provide 4 leg 10 dia stirrups. Okay. So first we have to find VUS. VUS is the shear force that is to be taken by the stirrup. That is given by this formula, B minus tau c BD. That is equal to 216.28 kilonewton. So shear for spacing of stirrups is found by this formula, 0.87 Fi ASV divided by VUS, where ASV is the area of the total number of legs. We have four number of legs. Area of 10 diabar is 78.5. Okay, and this is VUS. So we get this spacing is 340.71 Okay, but this spacing should be lesser of the this spacing should be less than maximum spacing, which and then that maximum spacing is lesser of these three. Okay, so 0.75 d is 457.5, 300 and SV to be found by this formula, that is 472.4 So list of this is 300. So we will provide 4 leg 10 dia stirrups about 300 center to center spacing as specified in table above. Okay, this thing is also specified in table above. Okay, so let's see in the detailing part. So this is the cantilever. This is the stirrups. Okay, so in this stirrups has to be provided at 4 leg 10 dia stirrups about 300 center to center. So this is 4 leg stirrups. There are 1 leg, 2 leg, 3 leg, and 4 leg, right? So this stirrups has to be provided at 300 center to center in this region. Okay, right. Now moving forward, check for shear at the face of cantilever at right. Okay, at a distance 5.6 meters from left. So let us find the shear force at a distance 5.6 meters. 5.6 meters, the shear force is 387. Okay, so 387. Okay, Shear force is 387. Okay. Now, provided AST one is 1005. Okay, we have provided 5 number of 16 diabars at this section. This is the tensile steel provided. Okay, so we have to take the area of tensile steel at this section. Okay, that is 1005, right? So AST provided is 1005 mm square. So PT is 0.258. Now permissible shear stress is 0.368 for this PT and M20 from IS 456 2000 table 19. Okay. The nominal shear stress again find V by BD. V is this. BD is known to you. This is 0.9923. Tau V is greater than tau C, but tau V is less than tau C max. So okay. So we have to find VUS, that the shear force which the syrups have to take. So as tau V is greater than tau C, so we will provide 4 leg 10 mm diameter syrups. Okay. So VUS is found to be 493.48. The spacing of stirrups is found to be 302.65 mm. Again, the maximum spacing should be lesser of these three, right? So the least is 300. So again, we will provide 4 leg 10 mm diameter stirrups about 300 mm center to center. Spacing by is in table above. So where in detailing we see in this region also, we provide 4 leg 10 mm diameter stirrups about 300 mm center to center. This is section 33. This is section 33, right? Now coming to the central beam. Okay. So check for the shear in the beam at the face of the support in the central beam. That is the distance 1.6 meters from left. So this is our central beam. This is one face. This is another face. The maximum shear force is at this face. So we will check for that. Okay. So that is 1.6 meter. So let us find the shear force from the table at 1.6 meters. Okay. So at 1.6 meters, the shear force is 651.6, right? So let us take 651.6. Okay. Let's see. Okay. Shear force at this is sorry, uh, 0.6 meter is 1.6 meters. Okay. Shear force at 1.6 meter, 1.6 meter. That is equal to 651.6 kilonewton. EST provided. Okay. EST provided in central beam is 4 numbers of 25 mm diabar plus 1 number of 20 mm diabar. Okay. So that is equal to this area as we found. Okay. 2 to 76.5. Okay. So this is AST provided. So PT provided is found to be 0.587. Okay. So permissible shear stress is 0.51 for this PT and M20 from table IS 456 2000 table 19. Okay. Now, nominal shear stress V divided by BD, that is 1.67. This tau V should be less than tau C max 2.8. So it is less. So okay. But this is greater than tau C. Okay. So we will have to provide 4 leg 10 mm diameter stirrups. So first let us find the BUS, that is the shear force that is to be taken by the stirrups given by this formula, that is equal to 552.1 kilonewton. Spacing is found to be 163. Okay, this spacing should not exceed, okay, list of these three. It is less than all these three. Okay, so we will provide 10 mm 4 leg stirrups about 150 mm. That is 8 numbers. Okay, on both the either side of the column, and the remaining area in between we will provide 10 mm 4 leg stirrups about 300 mm center to center. Okay, so let me explain this in through this shear force diagram. We can see in this central beam the shear force is maximum at support. Okay, as we move towards the center the shear force decreases. So we are providing 10 mm 4 leg stirrups, 8 numbers at 150 mm at this support, and 4 leg 10 mm dia stirrups at 8 numbers at 150 mm at this support, from this support, right? The remaining area, in between area, where we will provide a 4 leg 10 mm stirrups about 300 mm. Okay, because this nominal stirrups shear nominal stirrups are required in that area, right? So let us see the detailing. Okay, 10 mm stirrups about 150 mm 8 numbers from this support, 10 mm stirrups about 150 mm 8 numbers from this support, and the remaining portion you have to provide 4 leg 10 mm stirrups, 4 leg 10 mm dia stirrups about 300 mm center, right? So this is how you do the detailing of the footing. Okay, now we can see that I have provided face bars over here. Okay, so I have provided four face bars. One, two, three, four. There are four 12 mm face bars. Code says that when your beam is greater than 750 mm, then you have to provide face bar. Our beam is 750 mm, but still I am providing face bar because it will be helpful in taking torsion. Okay, so from that reason, I am providing this phase bar. We will provide phase bar whose total area is greater than 0.1% into of BD. Okay, equally distributed on each face, right? So I am providing four 12 mm diabars whose area is greater than zero point 0.1 BD. Okay, two on each face with spacing least of 300 mm or width of that. Okay, the spacing over here should be equal, but the spacing should not be greater than 300 mm or the width of the beam, whichever is less. So lesser is 300 mm. So this, if you calculate this spacing, turns out to be around about 240 or 250, something like that. Okay, which is less than 300. So it's okay. Now, coming to the point, now we will try to understand the theory of Perturband. Okay, how and when, at what distance do we cut this 225 mm dia bar? Okay, so for that, over here at the main beam, the main steel in the central beam is four numbers of 25 mm dia plus one number of 20 mm dia, and continuing bar in cantilevers are two numbers of 25 mm dia bar plus 1 number of 20 mm dia bar. So first we will have to find the theoretical cutoff point where we can cut these two numbers of 25 mm dia. Okay, so let's start. Calculation for curtailment of 225 mm diabars at the top of the midspan. The total number of bars at the midspan between the two columns, that is four numbers of 25 mm diabar plus one number of 20 mm diabar. We want to curtail 225 mm diabar and continue two number of 25 mm diabar plus one number of 20 mm diabar at the top of the cantilever on either side. So the area of the continuing bar is equal to 1295.25, and we want to find the depth of neutral axis because we want to find the MUR due to this continuing bar. Okay, so C is equal to T, C is equal to 0.362 FCK into XU, T is equal to 0.87 Fy into AST of continuing bar. Okay, because we want to find the theoretical cutoff point of two numbers of 25 mm diabar. So we will have to find the moment of resistance due to the continuing bar. Okay, so XU is equal to 107.65. Okay, so once you know the XU, you can find MUR due to the continuing bars. Okay, so 0.87 into Fy into AST of the continuing bars into D minus 0.461 XU. So that moment is 283.03 kilonewton. So we will find from the table what is the distance where we get this moment. Okay, so when we see this table, okay, then that moment is found to be between these two. Okay, that is it is found to be 2.55 meters. So okay, so from that we can see this is the figure. Okay, so this is the theoretical cutoff point. Okay, from here there are only continuing bars. Theoretically, theoretically require at this is the point where you can curtail the two numbers of 25 mm diabar and only continuing bars will proceed further, right? So we found that the moment due to this continuing bar is found to be uh, 283.03 kilonewton meter, which is at a distance 2.55 meter. So this is the distance 2.55 meters, and this will be the theoretical cutoff point of the two numbers of 25 diabar. So from this face of the column, this distance is 0.95. But the code says you cannot curtail the bars over here, but you will have to extend that bar for a distance L0. What is L0? L0 is, okay, L0 should be the greater of 12 times the diameter of bar, that is 12 into 25, that is equal to 300, or effective depth D is equal to 650. So larger of these two is 650 mm. So L0 has to be 650 mm. Okay. Now MUR by V. Okay. So this gives a distance dx from this point. Okay. And that point will be the point where the 25 two 25 diabars which we are going to curtail are fully stressed. Okay, point where the bars are fully stressed, because the development length given in our code is from the point where the bar are fully stressed. Okay, so this gives the point. This gives us the point. MUR by V gives us the point where the bar is fully stressed. So from this point we have to measure LD. Okay, so MUR we have already calculated, because we are taking MUR for continuing bar, because at this point, okay, the stress in the two bars which we want to curtail will be 0, but the stress in the continuing bar will be 0.85, 0.87 F5. Okay, so that is why we will take MUR for of the continuing bar, because the code says you have to find the moment of resistance for the steel which are fully stressed. Okay, at this section the fully stressed bar are the continuing bar. Okay, so we will find MUR for that, which we have already found, that is equal to 283.0 V. Now we have to find V for the for this section, that is at a distance 2.55 meters from the left, and that V is found to be from the table 315 0.85. So dx is 0.8961. Okay, so this is dx. So this distance is 0.8961 from here. Okay, at this point you get all the bars are fully stressed, right? Now we know code says LD should be less than MUR plus V, MUR by V divided plus L0, right? So L0 is 650, LD of 25 diabar should be in tension, okay? Should be less than MUR by V plus L0. MUR by V plus L0 is 1.5461 meters. LD for 25 diabar in tension from SP16, table 65 is 1175 This is less than this, so it is okay, right? So this is the point where you can curtail the 225 diabar. Okay, so I have written over here point where 225 diabars can be cut off. Okay, but I am taking this bars still further to the end of the support. So actual point where 225 diabars are cut off. Okay, so this is the theory of curtailment. Okay, so I am taking this steel up to the ends of the support and curtailing 225 diabars over here and continuing only this much in the cantilever. Okay, now check for deflection is not necessary in case of footing, as they are below the ground and are not going to be visible, but check for crack width has to be done, and the crack width should be less than 0.3 mm. Okay, so we will see this in the video which I will develop for crack width. Okay, I will try to explain the fundamentals in that video. Okay, so we can the table which I got in this for this problem was from the software. So that is just open combined footing. Okay, so member number is 1. Okay, press enter. Fi is 415, press enter. Fc is 20, press enter. LBC is 250, press enter. Length XL, total length XL is a total length that is 6.6 meters, press enter. Okay, thick depth of T1, first column depth is 600 mm, okay, 600, press enter. T2 is also 600, press enter. Width of column is 300, press enter. BW2 width is also 300, press enter. Total width of beam, okay, total width of beam we have given as 600, so 600, press enter. Okay, right, distance x, this distance x is 1.3 meters, okay, 1.3, press enter. Distance y, okay, so distance y is 4 meters, okay, so 4, okay, press enter. Now load on column 1 is 1200, press enter. Then we have to give factor loads and moments over here. 100, enter, okay, and 75, enter, 100, enter, 75, sorry, seven, load is, oh sorry, over here load is, this is load on second column, okay, sorry, this is 1200 again, okay, enter, and moment over here is 100, this is 75, okay, press enter, this is again 100, press enter, 75, press enter, okay. Now we will click, okay, okay, we have considered load factor as 1.5, okay, so this is the output, okay, so this is the table which I have taken from this uh, for this example, okay, in the demo video, okay. So you can make programs such like this which will be very useful, okay, and also we will be a great time saver, okay. So I hope uh, you must have found this video useful, and this is the complete detailing of the coding, okay. Thank you.